Okay, in the last video, we talked about derivatives and their uses mathematically and graphically and things like that. And we ended up coming up with this formula right here, which is a formula for the linearization of the function f of x at the point C. And again, like I had said then, don't get lost in the notation. That's the equation of a line in slope-intercept form. Don't do what I did when I was a student and get all mixed up. It's the equation of a line, the equation of the tangent line, actually. But well, suppose we actually, again, we can use this as an approximation, but the question becomes, that's great, why do I actually care about that? And I mentioned in the last video, one issue is nowadays we have computers and calculators that can do all the work for us. This was created a few hundred years ago when they didn't have access to that, so they had to come up with ways to solve problems that they could do out by hand. Working with lines is a whole lot easier than trying to work with cubics or fifth degree polynomials or exponentials or trigonometric functions. So there is a reason that they did this, and there is another way that this is actually useful. It's a trick that somebody came up with. And all of you know, going all the way back to pre-calc and even high school and maybe even junior high, a standard type of math question is, given a curve, say we have the black one right here, I want to find the zeros on that curve. How do I go about doing it? Nowadays, throw it into a calculator or a computer and done. A few hundred years ago, without that, one thing you could say is, well, suppose I pick a point x sub 1, and I know we kind of go back and forth with our notation, but now I'm going to call, instead of using c, I'm going to use x sub 1. I'm doing it because your book doesn't, I don't want you to get confused. So I'm going to call this point right here x sub 1, and I'm going to find the linearization. And I'm going to say, I have this point. That point is not a 0. I mean, I can tell just by looking at it. The function value is way up there. But I'm going to use that as an approximation, my linear approximation right there. That is not a 0. But this line right here is the equation of the tangent line right here. And that tangent line certainly does have a 0 right here. And clearly, if this is my first approximation for the 0 of this function, it's okay. That approximation is better. And now I will point out, there are times when this trick will not work. We'll look at those at the end of this video. This one is deliberately set up to make sure it works well. But if I could find the 0 of this tangent line, then I could use that 0, that x sub 2, as a better approximation of the 0 of this curve. And then if you're kind of getting the trick, well then I could say, if I have this x sub 2, find the tangent line there. Then find the 0, call it x sub 3 of my new tangent line. This is then a better approximation for the 0 than this one. And I can keep continuing, finding tangent lines and associated zeros that get closer and closer to the 0 I care about. Again, I stress, there are times when this will fail. We're only going to look right now at one where it will hopefully work for us. But this may seem a little bit cumbersome. I want to find 17 different tangent lines to approximate the 0 of that curve. But again, if you live a few hundred years ago, that's actually a good trick. Might take a little bit of work, but the other choice is to simply not be able to find an answer to the question. But I'm going to erase the picture now, since we kind of understand the process, because now we want to kind of work through this and see what we're doing. So I start with my linear approximation for x sub 1, and then I say there's another point on that line x sub 2 where the value at x sub 2 is 0. Plug that in here. The value of the line is 0, so 0 equals f of x sub 1 plus f prime of x sub 1 times this x is the x I care about, which we were calling x sub 2. At x sub 2, that's where I was getting 0. But now, since my goal is to actually find the value of x sub 2, algebraically find it. And I would point out, don't get confused here. I literally just plugged a point into my line. The point x sub 2, f of x sub 2, because f of x sub 2 is 0. But now, algebraically find this. So let's see. First, I have to distribute. So f of x sub 1 plus f prime of x sub 1, x sub 2, minus f prime of x sub 1, x sub 1. Now, I need to isolate this. So I'm going to subtract this over there and add that over there. I'll rearrange them, and I'll get f prime of x sub 1 times x sub 1 minus f of x sub 1 equals f prime of x sub 1, x sub 2. And again, don't get lost in the algebra. I'm just solving for x sub 2. I added this, then I subtracted that. And this is what I was left with on the right. Now divide the f prime x sub 1. Here, they'll cancel, and I'll just be left with an x sub 1 minus f of x sub 1 over f prime of x sub 1 equals x sub 2. And now I have a way to find x sub 2. And one thing I would point out, to find x sub 2, I need a point to start with. I can just arbitrarily pick that as an approximation. I need f of x sub 1. If I have the function, I can find f of x sub 1. I need the derivative at x sub 1. If I have the function, I can find its derivative. And then I can plug in x sub 1. Which means I can get this point by just picking an arbitrary x sub 1 to start. But now we understand, once I get x sub 2, I want to make my approximation better. I want to get x sub 3. But clearly, I could just go through this whole problem, replace all the x sub 1s with x sub 2s, replace the x sub 2s with x sub 3s, the algebra would work the same. And then I would get x sub 3 is x sub 2 minus f of x sub 2 over f prime of x sub 2. And then by extension, mathematically, we would keep this process going. It's called an iterative process. And we generally stop at x to the n plus 1, and we get x sub n minus f of x sub n over f prime of x sub n. And again, all of you should be used to this notation, the x sub n plus 1, 172 sequences in series and trig and all that. But again, now the idea is, given a function that I can find the derivative of, I can pick an approximation, a point maybe close to the 0 that I'm looking for, plug it in. From that, I can get an x sub 2, which hopefully is a better approximation. From that, I can get an x sub 3, which is hopefully a better approximation. And I can keep on going as much as I want to get as close to the 0 I'm looking for as possible. Again, there are times when this will fail when if you don't do it right, or if the function maybe doesn't work well for it. We'll see that later. But for right now, I want to work through this process. Hopefully it won't be too hard without a calculator. So, suppose we have a function, and I'm just going to write out, let's see, x sub n plus 1 equals x sub n plus f of x sub n over f prime of x sub n. So there's my little formula right there. Now we're going to use the function f of x equals x squared minus 4. Admittedly, I know the zeros there. That'll just help me see if my approximation is good. They occur at x equals 2 and negative 2. But we're going to assume, for whatever reason, I can't figure that out. So we are going to let x sub 1 equals 3. And hopefully I can try to get close to that 0 at 2. And now, just so you know, the way this generally works is you're told what your x sub 1 is, and then you're told find x sub 4, find x sub 5, find x sub whatever. And you just do as many iterations as necessary, showing